Okay, for this video, we're going to cover the rest of the materials that's going to show up on the final exam. So again, you do need the material on the midterm review for a comprehensive review, right? Because the final is cumulative. So this material starts at chapter 4. Anyways, so for the first problem, you're given a rational function and you are asked to find a horizontal asymptote, vertical asymptote, x-intercept, and y-intercept. Each one of these requires a slightly different technique and slightly different, result as the answer. So make sure you're, clear on exactly what you need to do. Horizontal asymptote, this is the easiest one because you just compare the degree of the top and degree of the bottom. Degree of the top is 1, degree of the bottom is 2, top less than degree of the bottom. So the answer here automatically is y equals 0. This is done by the case-by-case situation, depending on how the two degrees compare. You can take a look at that in the notes for 4.1 and 4.2. For vertical asymptote, you just simply set the denominator equal to 0. Set that equal to 0. This is very easy to solve. You can do it two different ways. You can simply just plus 16 on both sides. You get x squared equals to 16, and you just take the square root of both sides, but don't forget to put plus or minus. Okay, the small rule here is you must write your asymptote in the way of a equation of a line, a vertical line, which is simple enough, actually just equal to x equals to 4 and x equals to negative 4. Both of these are descriptions of vertical lines. For the x-intercept, this is where you set the numerator equal to 0. So x minus 3 equals to 0. And it's very easy to solve. So plus 3. We get x equals to 3. Now the rule here is you cannot write it as an equation. You have to write it as coordinate points, right? Because these are supposed to be locations. So the coordinate point is 3, comma 0, because the x-intercept always has y value equal to 0. That's your answer here. Last but not least, y-intercept. This one you plug in x equal to 0. So you just find f of 0, which is equal to 0 minus 3 over 0 squared minus 16. And the answer for that one is negative 3 over negative 16, which is equal to 3 over 16. Same idea though, you cannot write it as an equation, you have to write it as a coordinate. This time, because I'm talking about the y-intercept, x is 0, and y-intercept is, well, whatever number that you got. Okay, that's how you tackle all four of these situations. So all four of these parts of the question. Moving on to the chapter 5 material, find the exact value of the following expression. This is, once again, just a way for you to recognize of the cancellation property of log and exponent. We hopefully recognize 625. Write this on the side real quick, actually. 625. This is equal to 25 times 25. And these are equal to 5 times 5 each. So what that means here is 625 is just 5 to the 4th power. And the good news here is logarithmic base, exponential base, they cancel each other out. I just say 4 for the first term. Similarly, exponential base, logarithmic base, they cancel out. Just get 42. So the answer is 46. Easy peasy. The next problem type about calculating these kind of not exact answer for logarithm, you have to use the change of base formula. We're gonna change that to either ln of 30, right, log base e over ln of 7, or you can choose the common log, so log base 10, that is, of 30 over log base 10 of 7. Either way is gonna give you the same answer. All you have to do is punch that into the calculator, and it looks like let's see. It looks like about 1.7478, but it says 3-digit after the decimal, so 748. So this is just a quick application of the change of base formula. Number 4, we're going to use logarithm to expand the expression. So first thing here, logarithm is going to turn division into subtraction. So I'll have 25 x to the 8 y squared minus log base 5 cube root of d squared. And the top, there's actually a bunch of multiplications, so we're going to go ahead and break them all apart because logarithm turns multiplication on the inside into addition on the outside. Okay, and then while I'm at it, I'm also going to rewrite the last power into a fraction, right? Because d squared cube root is just another way of writing d to the 2/3 power. And the cube root is essentially the 1/3 power here. Okay. Now I do also know that 25, this first number here, is 5 to the second power. So what I really have here is, let me just write that out. 5 to the second power plus, and the rest I just copy and paste here for now. But basically, I'm going to apply the property logarithm that allows me to bring the power down to the front. And for the first one, I can even get that to cancel, right? Logarithmic base, exponential base, they cancels out. 2. But then the rest, I'm just going to move that exponent down to the front. Here. And same thing here. Okay, and that's the final answer. Everything expanded out. There's no exponents and then cancellation, whatever, allowed. Okay, going to number 5. This is the opposite, where we want to condense the expressions. And this one, in some sense, is kind of easier because all we have to do is use these properties in reverse, and there's less tricks to this situation. So I'll just take the 1/5 out, back up to the exponent. So I have log of z to the 1/5 power minus log of y, nothing happening there, and then this 1/2 power gets moved to the back to the exponent as well. So plus log of d to the 1/2 power. And the next step, the logarithm turns a subtraction into division on the inside. So I have log x to the 1/5 power all over y plus log of d to the 1/2 power. By the way, if you want, you can definitely rewrite that as a radical. Actually, maybe I'll do that at the end here. Same thing, this step, it turns addition on the outside into multiplication on the inside. I just have log x to the 1/5 times d to the 1/2 all over y. Let me write it slightly differently here. X to the 1/5 over y times d to the 1/2. Okay, but of course, for multiplication, you can just multiply the numerators together. And at this step, I will go ahead and write them into radicals. So 1/5 power is equal to the 5th root of x, and then 1/2 power is the square root of z all over y. That's the final answer here. Okay, not too bad of a problem. Really not that much things that could go wrong with this kind of questions. Moving on to the next problem, exponential equation. Right, this is something that we've been working with for a while. You can leverage the one-to-one property if you have it. If not, unfortunately, you have to use logarithm. So here, we realize 57 is not any sort of well-known powers 3. So we got to do ln on both sides. Okay. From here, this allows me to take that exponent, move it out to the front. So I have 2x minus 6 times ln of 3 equals to ln of 57. So all I have to do here is divide by ln of 3 on both sides. Plug that into the calculator. To be 3.68, and I plus 6 on both sides. 9.68, and of course I divide by 2 on both sides. So I got x is now approximately 4.8, 4.84. So obviously rounded to whichever digit that was required, but it's really not too bad to do from here. For part C, this is just kind of interesting just because it looks hard, but it's actually a pretty easy problem. It shows up on the homework as well, so it makes sense to be fair game on the test. All we have to do here is to use property of exponent to add the exponents together. So the left-hand side just becomes 2 to the power of 2x plus 1 plus 5x minus 6. At 64 at this point, we know that it is 2 to the 6th power. that means by one-to-one property, I can just drop the exponential base 2, or think about taking log base 2 on both sides. So I have 2x plus 1 plus 5x minus 6 equals to 6. And this becomes a section 1.2 problem. So combine like terms. Plus 5. And of course, divided by 7. My final answer is just x equals to 11 over 7. Very easy problem, consider how difficult it looks at the very beginning. Really the same idea for part D. I just want to mention it. I don't want to do this one. Save that for your own practice. Remember that division of the same base just leading to the subtraction of the exponent. Right? Just like what we did here in part C, but we have multiplication, so we add the power. Division, you just subtract the power. So really nothing new, nothing difficult from this kind of problem. Moving on to the last problem here. So for this kind of things, you want to get all the logarithm to the same side. So just plus log base 3 x plus 4 on both sides. So by property of logarithm, adding on the outside becomes multiplication on the inside. And then the right hand side just equal to 2 now. All there is left. And from here, to get rid of the logarithm, we exponentiate both sides. This way, the exponential base and logarithmic base cancel out. We have whatever's inside that bracket, so it's 3x minus 1, x plus 4. And on the right hand side, we just have 3 to the second power, which is just 9. Now this become a section 1.4 problem again. So let's just FOIL. 3x squared, 12x minus x minus 4. And then I might as well just clean everything up. So minus 9 on both sides here. So I guess 3x squared plus 11x minus 13 equals to 0. The space here a little bit. Now this one I don't think is factorable. Yeah, just because 3 and 13 only have one factor and there's no good arrangement of these that will get you there, that will get you to have the perfect factor. So in this case, you just hit it with the quadratic formula. We'll move on to the next problem a little bit. Use up that room. But I'm going to apply the quadratic formula here, which is negative 11 plus or minus, let me write the x first. Negative 11 plus or minus square root of 11 squared minus 4 a and c, which is negative 13. All over 2a. And again, as soon as you copy down the formula correctly, the numbers are not going to be too big of a deal because you have calculators. characteristics. And yeah, um, that is not a perfect factor. 277 over 6. If it's not a perfect factor, then we can just leave it as is. You don't have to worry about simplifying this expression more. Okay, so that right there is your answer. There's nothing wrong with it. It's a perfectly good answer. Okay, so that's it for this kind of problems, and that's it for this final review. I think this is all the problem types that we need to cover for the final, and hopefully these videos help, and hopefully you learn some stuff before you have to take the actual exam. And hopefully, again, I'll see you guys next week for the next module of this course.